Hello. Today we're going to talk about Chapter 16, Probability Models. And the basis for those is the Bernoulli trial. Essentially, there are two outcomes, success and failure. All right. More basic than that is you can think of flipping a coin, heads or tails. The probability of success is always constant, and the trials are independent. However, okay, if the trials aren't independent, we can keep going as long as our sample is less than 10% of the population. Okay? Think of it like you're sampling people at the mall. All right? People that come in and out of the mall at one entrance. Well, what if you get one of those people again? Okay? So if as long as your sample is 10% of what your population is, you're okay, because odds are there's somebody else like that person. So just because they decided to do the survey twice, well, odds are there's probably another person that would have voted the same way. Okay? That's kind of how I think about it. Okay? So the 10% condition is okay, as long as you're under that 10% mark. All right, and this is, of course, just a fun little comic because I just love Calvin and Hobbes. Okay, so let's do some examples. Are these Bernoulli trials? Okay, so we have 5 males and 8 females. We write their names on paper, and we choose 4 of them out of a hat. Okay, we count the number of females who are chosen. Is that a Bernoulli trial? Well, most certainly not. All right, because once I pick somebody out of the hat, it changes the outcome afterwards. Okay, so it changes every single time. All right, well, what about the next one? 1 in every 90 pregnant women gives birth to twins. We count the number of twins born to a group of pregnant women who work in the same office. All right, well, yeah. All right, every person is independent. Okay. We're doing just one sample, so that's got to be 10% of, it's got to be less than 10% of all pregnant women, and, well, choosing women is also independent. Okay. All right, we count the number of times a woman who has been pregnant 3 times has given birth to twins. Well, no, because women who have twins are more likely to have them again, so that changes the outcome. Okay, they're not independent. We pick 40 M&Ms at random, counting how many of each color we get. Well, counting each color is more than 2 outcomes. We can't do that. We need 2 outcomes, either blue and not blue. Okay. Next one, Towns Merchants Association says 26% of all businesses there are owned by women. You call 15 chosen from 77 in the yellow pages, counting the number owned by women. Well, hopefully you caught that. 15 out of 77, that's more than 10% of the population. We don't like that sample. All right, so those are examples of, what isn't a Bernoulli trial. So usually with Bernoulli trials, we don't just look at a single trial. We look at a geometric one, and that's like saying, how many times do I have to flip a coin until I get a tail? Okay, that's what we're looking at. Okay. Now, here are your formulas. So, Q is your probability of failure. Your expected outcome is your mean times 1 over P, where P is your probability of success. Your standard deviation is this. Okay? Just understand knowing your values is important. As always, let's do some examples. So, they report 91% of emails are spam. Let's assume your email is typical, you're not using a spam filter, and spam comes from everywhere, so we'll consider them independent. When you first check your email, how many spam emails should you expect to have to go through before you find a real one? So the formula was the expected outcome is 1 over the probability of success. We want a real message. Probability of success has to be 9% because 91% is spam. It's either spam or not spam. So this is how we get our expected value. So on average, I have to check over 11 emails, so 12 emails, until I find a real message. What's the probability that the fourth message is the first one that isn't spam? So I'm going to have 3 messages that are spam, and then the fourth one is spam. So we write it like this. Okay, that formula was a little confusing. Think about it. 3 failures and 1, you can think of this as a 1 here, success. Then we get our probability. So slightly less than 7% chance that my first real message will be the fourth one I check. Okay, so not very good odds. But remember, that's if the fourth one is a real message. It didn't count if the first, second, and third. All right, so let's talk about the binomial model. All right, so this counts the number of successes in a fixed number of Bernoulli trials. So, like, what are the chances of flipping a coin and getting 3 heads in 12 tosses? Okay, so it doesn't matter where you get a head coin flip, either in the first try, second and third, or the first, fifth, and 12th try. But you're looking for 3 out of the 12 to be successful. That's what a binomial model is. Okay, so this is the formula. You want to know that this is read as N choose K. So, what did I say? 10 emails, choose 3 of them. Okay, and this is how you do, that's the formula. So N factorial. Let's do an example. Let me get my pen. So let's say we had 5 factorial. That's just 5 times 4 times 3 times 2 times 1. Okay. If we did 3 factorial, that's just 3 times 2 times 1. Okay. We always stop at 1 because if we kept going, the next number would be 0, and it doesn't really matter where we keep stopping because that would just all be 0. So that would be kind of a waste. So we stop at 1. Okay, so that's how you can do a factorial. Now that we understand N choose K, we're going to use our binomial model. So this is the probability of something occurring. Okay, and we use this formula. Okay, so still similar before, but now we're just adding that N choose K in front. Okay, with the mean of this and the standard deviation of that. Always, we're going to do an example. Okay, so global security company, 91% of the emails are spam. You have 25 messages. What's the mean and the standard deviation? So we go to our formula. Expected outcome is 2.25. Okay, 25 message times the probability of success. Standard deviation is the square root. 25 messages times the probability of success, probability of failure. So we read that as, among 25 email messages, I expect to find an average of 2.25 emails that aren't spam with a standard deviation of 1.43 messages. Okay, I know that sounds weird because we're talking about 0.2 and 0.4, but you're talking about probability. Okay, kind of think of it like that. So what's the probability that you'll only find 1 or 2 real messages? So we find the probability of 1 and add it to the probability of getting 2. Another way of writing N choose K is with these parentheses. Okay, so you're going to put N on top and K on bottom. That's the same thing. So 25 choose 1, all right, because you want one real message. So 1 success, 24 failure, plus 25 choose 2 real messages, 2 for success, 23 for failure. Then you add those up. So a little over 50% chance that 1 or 2 of my 25 emails will be real messages. Okay. All right, so we really need to understand the difference between binomial and geometric. Okay, so let's talk about flipping a coin, where success will be getting tails, and we're going to flip a coin and we're going to do it 5 times. All right, so binomial PDF would be flipping a coin. All right, what is the chance of getting 3 tails in 5 flips? So 3 tails in 5 flips. So that is 5 trials. Success, all right, probability of success, so probability of getting a tail would be 1/2. And our X value would be 3. So just getting 3 tails. Doesn't matter where I got them. The first flip, third flip, and fifth flip, or the first, second, and third. Don't care where, but I got 3 tails. Binomial CDF is 3 or less. So getting 3, 2, 1, or 0 tails in 5 flips. So 3 or less. We would do 5 trials, 1/2 probability of success, okay, or 0.5, and the X value would be 3. Notice these look the same, so be careful, okay? Binomial is exactly 3, CDF, right, so PDF is exact, CDF is or fewer. Now for geometric, let's say the first tail, okay, so the first tail is on flip number 3. Or let's stick to 5 flips, so flip number 5. Okay, so here, oh, I meant to get rid of those. Those aren't the same for what we're doing. All right, so the probability of success is 1/2. The X value is on flip number 5. So that's all we got to do. Here, the first success is on or before trial X. So the first tail is on flip number 5, or 4, or 3, or 2, or 1. Wouldn't be or 0 because you have to actually flip to get a tail. So the probability of success is 1/2, and our X value is still the same, 5. So that's why I'm saying be careful. Okay, these look the same, but it's one slight difference. It's PDF and CDF. CDF and PDF. All right, make sure you know the difference. Okay, so when dealing with a whole lot of trials, like let's say I wanted to flip a coin 1,000 times, okay, doing direct calculations, gross, don't want to do that by hand. So we use the normal model, okay, which is pretty handy. However, we have to be careful because there is a condition, always a condition with statistics, is that we have to have at least 10 successes and 10 failures. So the number of trials times the probability of success must be greater than or equal to 10, and the number of trials times the probability of failure has to be greater than or equal to 10. And I just had to throw this in here because, you know what, people say all the time that statistics is so easy because look at this math. I mean, two numbers have to be bigger than 10. That's so easy. All right. Yeah, the math might be easy, but stat is useless if you don't understand it. Okay? So things are starting to get a lot more complex. So please feel free to ask me questions because if you don't understand what's happening, good luck, child. All right? Let's keep going. So to start with, we are talking about continuous random variables. So we're using it to approximate a binomial model. Therefore, we can't do exact values. Okay? We can't do probability of exactly one thing happening. It has to be between two things. So greater than, less than, between two numbers. So let's do an example. So here, again, the company reported 91% to be spam. You observe that the filter okayed only 151 of 1,422 emails. All right, so is this too aggressive? What's the probability that no more than 151 of those emails are a real message? So we assume the message arrived randomly and independently with a probability of success of 0.09. The binomial model applies, but it'll be hard to work with. So let's check the conditions for the normal approximation. I see that the messages represent less than 10% of all email traffic. Okay. I expect NP and NQ to be greater than or equal to 10, which is definitely true. So it's okay to approximate using a normal model. So doing that, we find the mean and the standard deviation, and I would draw a picture. Okay, that always helps me. So again, right here, we want that z-score. All right, our mean value has to be we want it at 151. What's probably being more than 151. So we get our z-score, calculate it, 2.13. Okay, which means among my emails, there's over a 98% chance that no more than 151 of them were real messages. So down here. So the filter might be working properly. Okay, that's a whole lot of spam. Okay. Okay, so let's do some examples. We have an archer is able to hit the bullseye 80% of the time. She shoots 6 arrows. What's the probability of each of the following? Her first bullseye is on the 3rd arrow. So the first success is on the 3rd hit. So we can do a geometric. Her first success is on the 3rd arrow out of 6, right? So here we can do it by hand. All right, 2 success. I'm sorry, 2 failures and then a success. All right, first bullseye is on the 4th or 5th arrow. So probability of the 4th, probability of the 5th, probability of both. Oh, well, that's a typo. That's supposed to be, oh, and now I just gave the other one away. Cool. So for +5 gets a probability of less than 1%. Okay, so she's got some pretty great aim that the first bullseye is likely not on the 4th or 5th arrow. So what's the odds that she misses the bullseye at least once? Well, at least once is easier to approximate if it's only one, or the opposite, right? So we do 1 minus the probability of it not happening. So that's 73, well, almost 74%. Okay. All right, so here's some more examples. Practice with these. Let's see if you get them correct. She gets exactly 4 bullseyes. You could do it this way. She gets at least 4 bullseyes. Bullseyes. Sounds weird now. Okay, hold on. Make sure that you understand this. This is getting exactly 4 bullseyes out of 6. Okay, so 6 choosing 4, we don't care when the 4 happen. All right, probability that she gets at least 4 bullseyes. Okay, so she can have 4, 5, or 6. We can calculate them individually and add them up. Okay, or do 1 minus the binomial CDF of 3 or less hits. Okay, getting 3 or less bullseyes. You could have done it that way. She gets at most 4 bullseyes. Well, you could do the binomial CDF. So this is this probability. Hopefully this is making sense. If not, ask me in class. Okay, but it's just knowing which calculation to use. Okay, so knowing what the meaning of each. Okay, so let's do some more. How many bullseyes do you expect her to get? So you got to think about your probability model. Okay, your expectation, right? So expectation, the number of times the probability of success. So 4.8, almost 5 bullseyes. All right, do your formula for standard deviation. And if she keeps shooting until she hits the bullseye, how long do you expect it to take? Okay, so how long until she hits her first bullseye? So the expectation is 1 over the probability of success. So it's 1.25. So really just 1 hit. Okay, 1 or 2 hits. She's a great archer. Oh, of course we're not done. So let's find the mean and standard deviation now that we're doing 10 arrows. Okay, so the mean and the standard deviation, we would multiply the variance and the mean by 10. Okay, so that n would be 10. What's the probability that she never misses? No misses is the same as all hits. So we get 0.107. So that would just be 0.80 to the 10th power. All right, there are no more than 8 bullseyes. So probably it would be less than 8. Exactly 8 bullseyes. Okay, she hits the bullseye more often than she misses. So probability has to be more than 6, right? Because if it's got to hit more than she misses, so she can hit blah, blah, blah. Have 6 hits and 4 misses, 7 hits or 4 misses, 8 hits, 9 hits, or 10. Yeah, I know. You thought it was over. So an archer is able to hit them 80% time, 200 arrows. Now what's the mean and the standard deviation? Oh, lo and behold, now the numbers are changing. Okay. All right. Oh, that's supposed to have standard deviation. Let me fix that. There we go. Sorry about that. So the standard deviation is this. And is a normal model appropriate here? What you think? Yes. Okay. Because n times p and nq is greater than 10. Okay, you get 160 and 40. All right, I know, last one. So, using your normal probability, describe the distribution of the number of bullseyes she might get. So, about 68% of the time will be between this and this. We took the mean and we subtracted 1 standard deviation and added 1 standard deviation. That's the range. For 95% of the time, it would be 2 standard deviations. So the mean minus 2 standard deviations is here. The mean plus 2 standard deviations is here. 99.7 is 3 standard deviations. So get the mean, subtract 3 standard deviations, add 3 standard deviations. That's how you describe it. Okay? It really is that simple. So, would you be surprised if she only made 140 bullseyes. Well, 99.7% of the time, I would expect it to be between 143 hits and 176 hits. So yeah, I'd say that's pretty rare. Okay, we can actually find the probability with our z-scores. And yeah, that's more than 3 standard deviations below the mean, right? It's less than the mean by a whole lot. All right, so that's really bad day for her. Okay, very unlikely to happen to her. Okay, so what can go wrong with Bernoulli trials? So you need 2 outcomes per trial. Okay, a constant probability of success and independence. We talked about this on the first slide. You also want to remember that 10% condition. Okay, don't confuse geometric and binomial models, and don't confuse the PDF and the CDF. Don't use the normal approximation with a small n. Remember, you need 10 successes and 10 failures to use the normal approximation. Okay, kind of a short chapter. I hope this makes sense. Okay, talk to me in class, all right? Probability is real weird.